Hello. Let me first congratulate you on making it and being enrolled in the course of calculus. You've worked hard your entire high school career to get here, and I want you to get a little snapshot of what you're going to be studying over the next 2 semesters in this course. Calculus is a beautiful mathematics. According to Richard Feynman, who is an American physicist known for his work in quantum mechanics, calculus is the language that God talks. We're going to find out exactly what Feynman was referring to when he said that, but I'm going to ask you a question now, and then I'm going to ask you that same question at the end of this presentation. Let's talk about where you're at right now. If someone were to ask you what is calculus, how would you answer that question? You might have had a little exposure to calculus, or maybe you've had none at all. But what have you heard about the subject of calculus? This presentation is taken from a book called Infinite Powers, written by Steven Strogratz. He's a professor of applied mathematics at Cornell University, and he's regarded as one of the most highly cited mathematicians. According to those that know him, Steven Strogratz is the best mathematician among writers, and the best writers among mathematicians. So let's think about this. If we didn't have calculus, if calculus was never created or invented, what would life be like without calculus? Well, we wouldn't have any cell phones. We'd have no way to put 1,000 songs in your pocket and have them accessible to you at any given moment's notice. There'd be no GPS, there'd be no ultrasound, and there'd be no unraveled DNA. All of these things have to do with calculus. As a matter of fact, the discovery of the planets is directly related to the study of calculus. So calculus is this. It is a single, big, beautiful idea that runs through the subject from beginning to end, and that idea is infinity. Now, infinity is a concept. And once you're aware of the idea of infinity and its role in calculus, the structure of calculus falls into place. This is called the infinity principle. Calculus is utterly obsessed with simplicity. And that might be hard for you to grapple with right now, because you've probably heard that calculus is a rather difficult mathematics. But what it sets out to do is to make very hard problems extremely simple. What we can't take away is the bulkiness. There is going to be some new notation that you're using because we're working with very difficult, complicated problems. But we're going to tackle these problems in a simplistic way. And then we're going to solve these problems. Some of the most difficult, important problems that the human race has ever faced. We do this by taking a very big, complicated problem and we break it down into smaller parts. And not just small parts, but we go smaller and smaller and smaller. So instead of using just digestible chunks or bite-sized pieces, we keep cutting it down and cutting it down and cutting it down. And then we have infinitely many of these tiny conceivable parts that we could then problem solve. And then what we attempt to do is put all that back together. So it solves the problems for all the tiny parts, which is usually pretty easy. And then we take those tiny parts, as you can see in this little video clip, and we put them back together to make a beautiful solution to a complicated problem. So in this infinity principle, the infinity principle will shed light on any continuous shape, object, motion, or phenomenon, no matter how wild and complicated it could appear. We're going to reimagine this as an infinite series of smaller parts. We're going to analyze those smaller parts, put the results back together, and solve the original problem. Infinity, which is a concept, can be a big headache for many of us. And it's true in calculus too. It's confusing because infinity doesn't have a value. Infinity has no end. Infinity is a concept. And if you're not quite sure of the concept of infinity at this moment, as you go through the course, you're going to understand infinity a lot better. It is essential to understanding how calculus works, and it leads to correct answers even when we sometimes can't explain why those answers are what they are. Calculus has logic and intuition. Logic is a way of using a set of concrete rules and formulas that you have learned over time to come up with a decision. That's what logic is. But intuition is something that you have built inside of you that kind of guides you along the path to make sense of problems as you go. Logic always lags behind intuition, meaning you're going to have some idea of what a solution to a problem is before you actually can figure out logically how to solve it. And that's very normal. And that's one of the things that you're going to see as we go through this course in calculus. Now, we're going to talk about curves. And we talk about curves right away in calculus. It's one of the first things that we study. Determining a perimeter and surface area of round things is extremely brutal. Triangles and squares, pretty easy. They're composed of straight lines and flat pieces. It's easy to figure out perimeter area and volumes on shapes with a small number of corners. But when you try to do this with something round, it gets very complicated. So where calculus was actually generated from was the curiosity of some of our greatest thinkers and their frustration with the concept of roundness. But here's what we know. Curves are actually made of straight pieces. What do I mean by that? If we take any graph, or any curve for that matter, and we zoom in on that graph, we can see that if we zoom in enough, it tends towards a straight line. And this is going to be one of the most important things in calculus that we study, is that we can take any curve, anything that's round, and we can make it linear. At that point, we can calculate whatever we want by adding up all of these tiny straight pieces. And then again, we put them back together to get an idea of the behavior of the curve itself. Now, some of our greatest thinkers and mathematicians worked on these ideas of taking something curved and making it straight for centuries and centuries. Think about this: a javelin flying through the air, a ball rolling down a ramp. These are all things that have to do with motion, and this is the second part of calculus that we're going to study. How do things move as a javelin is flying through the air? What's happening to that javelin? Or a ball rolling down a ramp? What's going on with the velocity? Kepler, who discovered many of our planets, fell into a state of self-described sacred frenzy when he found his laws of planetary motion. He was having a hard time understanding it. The movement of the Earth and other planets in our solar system have to do with the mystery of motion. And again, his logic was always behind his sense of intuition, which is very normal, and this is what you're going to see as you go through the course. Motion problems were worked out by mathematicians well before calculus was ever invented. Trivial motion problems, which is a constant speed, you've studied these in Algebra 1 and Algebra 2, which is just distance equals rate times time. That's pretty trivial. But what happens when the speed changes? Nobody could explain the patterns, at least with the existing forms of mathematics back then at that point in time. So when speed is changing and not always constant, here comes the infinity principle once again. Motion at a changing speed is made up of infinitely many brief motions at a constant speed. And this is the idea of zooming in on a graph of a curve. We can see that that curve becomes linear. So we can take this very complex motion problem, how a javelin changes its velocity as it's thrown through the air, or a ball rolling down a ramp, and we can zoom in on that and find smaller motions of constant speed. Now, this is where the mystery of our curves collides with the mystery of motion. Isaac Newton, who gets credit for discovering calculus, he made his mark on the world like nobody before his time and nobody since his time. He figured out how to put these pieces of a curve back together. So mathematicians before him figured out, okay, we can zoom in and find this straight line, but how do we reverse that process and put everything back together to solve the problem? That was something that was highly complicated and unknown. What Newton did is he found a way to quickly and easily put that back together, and that was his gift to the world. His method that he used, which we will be studying, can be used with any problem involving curves and any problem involving motion, and that's what made it so special. Instead of just using specific problems with curve and specific problems with motions, we can take any situation, use Newton's methods, and solve these problems. He explained that the arc of a cannonball and the orbits of the planets revolving around the sun are used or can be solved or can be explained using calculus. The final thing we're going to be looking at is the mystery of change. Trajectory design. You saw this in Hidden Figures when Katherine Johnson, who was one of the first, if not the first, group of black women working for NASA. Stock market patterns, the mystery of change. How can we figure out patterns in the stock market? Weather forecasting. Again, a mystery of change. All of these things can be described or can be solved or can be studied using calculus. Population changes is another one. How the blood flows throughout the body. All of these things would never be explained without the mathematics of calculus. And so maybe now you have a little insight as to what Richard Feynman was saying when he says calculus is the language that God talks. And so we're going to ask you one more time. After viewing this presentation, how would you describe calculus? What is it?